All right, so just the story so far. So let's just sort of recap where we are. So what we've accomplished is we have this linear program with a reasonably small number of decision variables. Where the whole point is, right, that we phrase everything only in terms of the interim allocation and payment rules. And so what are the constraints? We have the Bayesian standard compatibility constraints. Those are easy. The individual rationality constraints are easy. And then we have these border constraints saying that 1 is at most 2. There aren't too many of these incentive compatibility constraints. They're just for all I, for all true types, for all reported types. There are even fewer individual rationality constraints for all bitters, for all true types. There's a ton of border constraints, tons of them. Okay, so these are for all j, all items, and then for each fixed j, you have to have a choice of the restricted set of valuations. Okay, so certainly exponentially many constraints. Okay, and then right, non-negativity. And feasible solutions are exactly the reduced forms. And remember, reduced form is just the fancy word for the y's and the q's. Okay? But the point is they're actual y's and q's induced by bona fide mechanisms xp. Okay? So we have a linear program, you know, with much smaller dimensions that does indeed capture all of the reduced forms. And I think it's useful to have a sort of, you know, very coarse geometric view of what's going on. Okay. So the geometric view is a projection. Okay? And again, as you've seen, because all of the complications are with feasibility, and feasibility in the problems we're studying only references the allocation rule, I'm often just going to ignore the p's and q's. I'm just going to focus on the x's and y's. That's where all the hard stuff is. So in general, what we're doing is we have this high-dimensional set of x's. This is my attempt at a high-dimensional polytope. Okay. And then we're projecting it onto a lower dimensional space. Okay? So these are the y. So I'm going to call this set x, and these are the y's, which I'm going to call capital Y. Okay? And so this mapping, so just to be clear, so what is this projection? So the xij v arrows, so this is the x post allocation rule, are inducing the yij vi's via this average. Okay, so just this weighted sum. So this, again, is just the definition of the interim rule. But again, what I want to emphasize here is just, this is just some linear function. Okay, so we get the y's by just applying some, you know, linear projection type operator to the x's. So this is basically what's going on. So this high-dimensional polytope, we had an explicit description of. That's what we started today with. Okay, that's when we had the variables, the x's and the p's indexed over all of the valuation profiles v. So it was huge dimensions, but it was very easy to just write down all of the constraints. Okay, so we had this exact character. We had an explicit description of what this was. So then, what did we do? So then we said, let's pass to the interim rules. So we basically figured out what dimension we wanted, what the variables were. And what we just did is we just figured out an explicit description of the projection of this polytope. Okay, so we said, take all the real allocation rules, project them into the y's, and now, you know, what happens to the constraints? And can we get a handle on what those constraints look like? And this is them. Okay, so these are exactly the defining half spaces for the projection of the polytope. Okay, so that's what this is. Explicit description of the projected polytope. All right? Okay, so that's just worth kind of keeping in mind as a rough guide, because we're going to have some geometric arguments in this lecture. Now, remember, so in this lecture, what I want to focus on is, really structurally. Can we have an analog of, can we have some version that says revenue reduces to some variant on virtual welfare maximization? And I claim, if you think about it, here would be the best case scenario. So a special case of what we're trying to do is the single parameter theory, which requires virtual welfare maximization. We've seen even in a single buyer, we need randomization. So what would be the simplest imaginable description of optimal auctions? Well, I guess it would be a randomization over virtual welfare maximizers. Okay, that's kind of the conceptually simplest thing we could possibly hope to be true. And shockingly, it actually is true in problems we care about. Okay, so that's going to be the point of this lecture. So best case scenario, opt auction is a distribution over virtual welfare maximizers, which I'll define exactly what that means a little later. Okay, so VWMs. So the two things that are going to be more complicated than in the single parameter theory, first of all, there's the randomization, but we know that's necessary. The second thing is, and this is not surprising, we're not going to have some formula. We're not going to have this V minus 1 minus capital F divided by little f. I mean, that's just way too good to hope for. So the analog of those virtual values is just going to be computed from some linear program. Okay? But once you compute it, it gives you the functions, and then you do a suitable randomization, and you're good to go. Okay? All right, so at the same time, I'm going to go beyond additive. Okay? And I'm not going to define generally, what one can handle, but I just want to think about this representative special case of unit demand bidders. Okay. Yeah, so not additive is the point. And if you think about it, this already, so what we did last lecture does not apply to unit demand bidders, okay? And the reason is because for unit demand bidders, we basically want to add some constraints to the original ex post linear program, the high dimensional linear program. Okay, so change in the non-reduced LP. So remember, unit demand bidder, so again, like additive bidders, you have these VIJs, but when you get a bundle, you don't take the sum, you take the max. And the way we normally think about that is like, well, okay, if people only want their best item, let's just only give them one. And so you usually just restrict allocations to give each bidder at most one item. And then it's basically like bipartite matching, right? So if you think about that, you're like, okay, so now back in the original non-reduced LP, last lecture we had the constraint that every item was allocated to only one person. That made sense. Now we just want the other set of constraints that every person only gets one item. Okay? So for the non-reduced LP, we want to add, and so remember, this is in terms of the x's, this original LP. So we add that the total, so the goods given to a given bidder is at most 1 for all I in V bar. Okay? So geometrically, what we just did to pass from additive valuations to unit demand valuations is we took our high dimensional polytope and we added some more constraints. Okay? Actually, kind of a lot more constraints, because there's one of these for every valuation profile. Okay? So that means that this projection is going to look different. And it means that the border constraints are no longer in general going to characterize all of the reduced forms that we care about. Okay? So last lecture, we had some y's, so that's in the projected space. And we said, when is there an x that induces them? So we're asking exactly the same question now, except the x's we have in mind are more constrained than they were before. Not only do they only give an item to one person, they only give one item to a person. Okay, so not right. So the question then is, how does this change in the high dimensional polytope get reflected in the low dimensional polytope? Okay, so this works for additive bidders. what's the analog for, let's say, unit demand bidders, or much more generally. Okay? Okay, so those are some of the motivations about what we're going to do and the issues that we're going to solve. So let me tell you what's really kind of the main point of this lecture. Okay, so the main structural theorem, and this is barely a year old, so this is Kai, Daskalakis, and Weinberg from Fox 12. So, and again, I'm going to state this for unit demand bidders, but it's, it is more general. Basically, the assumption you need is that the bidders are additive, but that there's also allocation constraints. So a sort of weird way to think about unit demand bidders. You can think about it that my valuation is actually additive, but just the mechanism's only allowed to give me one item. Okay? And then that's actually equivalent to being unit demand, okay, once you have the allocation constraints. So anytime the valuations can be so expressed as additive, but with additional constraints on the allocation, then what I'm going to talk about today works. Okay? So it's not all the applications you'd want to care about, but it is somewhat general. Okay? All right, so here's the claim. So every vertex y of y. Okay, so remember y here is the projected polytope. Okay? So I'm saying consider the polytope of reduced forms, okay? And consider a vertex, a corner. Okay? The claim is every corner of this projected polytope is induced by a virtual welfare maximizer. Okay? So I'll tell you exactly what a VWM is in a second. But again, just to be clear, I'm saying pick a corner of the projected polytope in this unit demand setup. Look at everything that projects to it. And there may be many, right, when you do a projection, it's not injective. Okay, so many things from the high dimensional polytope may map to the same point in the low dimensions. But I just claim I can find something in high dimensions, that is, I can find an actual allocation rule, which is a virtual welfare maximizer that projects to this particular reduced form at the vertex. Okay? So then, I don't expect you to necessarily know what to make of this, but this actually implies what we want, and I'll explain why it implies what we want. This gives us an analog of Meyerson's theory, basically. All right, so what's a virtual welfare maximizer? So a virtual welfare maximizer is an allocation rule, X, that maximizes, it's what you'd think. So basically what it does is it looks at the input valuations, it applies some transformation, which I'm going to call phi in the spirit of last quarter, and then it just maximizes welfare with respect to these transform valuations. Okay? And so the free parameter is this phi, this transformation. Okay? So that maximizes over feasible allocations. And where the phi ij's are arbitrary functions. Okay? So for example, suppose it was unit demand bidders. Okay, and again, unit demand in this context, we're thinking of just like the allocation should be a matching. Okay? So then what does a virtual welfare maximizer look like? Well, up front, it pre-commits to some function's phi ij. Okay? And so basically when bidder I shows up and it says, oh, my value for the three goods are 3, 5, and 7, then we invoke the virtual valuation function. It says, oh, in that case, I'll give you weights 10, 2, and 6. For the items 1, 2, and 3. Okay, so the phi takes as input your value for each of the m items, and it spits out your weights for each of the m items. Okay, so that defines your phi ij's as a function of your report. So now, for each bidder item pair, we have a weight, okay, so the output of the phi ij on that particular item. And now we just compute a mass matching with respect to those weights. So that's a virtual welfare maximizer. Okay? So there's some table lookup as a function of what people report, what weight you ascribe to particular edges, and then you just do max weight matching. Okay? Now there's a lot of these because there's a lot of lookup tables. There's a lot, there you can basically have arbitrary freedom of mapping the v's to the weights, to the phi of v's. Okay? But for a fixed choice of phi, it's just a very simple deterministic mechanism. Okay? And in the unit demand case, easy to implement in polynomial time. Okay? Because again, really this is just doing welfare maximization. And the phis just tell you what weights to feed into the black box that does welfare maximization. Okay? Definition clear? All right. And so in the, in the single parameter case, there's only, we usually think about there's only one item, so there's no j. Okay, so in the Meyerson theory, there's no j. And then phi was a particular function that we wrote down explicitly. Okay? But with those additional simplifications, it was indeed a virtual welfare maximizer. Okay? All right, so let me now explain why this main structural theorem gives us an analog of Meyerson's theory. Okay? And it's not too hard. Okay? And then I'll prove the theorem. Okay? Yeah. So corollary, so two corollaries. And we'll have kind of everything we want. So for every allocation rule x, so remember capital X is just the non-reduced LP. Capital X is just the polytope of all allocation rules that are feasible. Okay. So for every feasible allocation rule x, the claim is there exists a distribution over VWMs. So remember, virtual welfare maximizers live up here. Okay? They're real mechanisms. They're not interim. Right? They really are operational. They tell you what to do on every input. Okay? So VWMs live up here. Consider an X, which lives upstairs. The claim is there exists a distribution over VWMs little x prime, which is a convex combination of virtual welfare maximizers, is also an allocation rule, and in this polytope capital X, so that x and x prime have the same reduced form. Okay. So don't forget, when you're doing a projection like this, it's not injective. Okay? So many different mechanisms can go to exactly the same point downstairs. That is, many different mechanisms can have exactly the same reduced form. So what I'm saying here is, give me any mechanism you want. Okay? I'm not claiming that that mechanism has to be a distribution over virtual welfare maximizers. That need not be true. But I am claiming, well, if all we care about are reduced forms, then this thing may as well be a distribution over virtual welfare maximizers. Okay? I can find one that has exactly the same reduced form. Okay? So that's what I'm claiming. So, okay, so why is that true? So that's basically true by linearity. So start from x, okay? And so the original allocation rule, so it has some reduced form, okay? In any polytope, right, any point can be written as a convex combination of the vertices, right? So I don't know how much basic polytope theory you guys have seen, right? But, so in 2 dimensions, anything inside, not only can it be written as a convex combination of the vertices, but in fact, you can always find at most dimension plus 1 vertices of the polytope, so in this case, a triangle. So that if you take the suitable convex combination of these vertices, you can get that point in the interior. Okay, so polytopes, there's a duality in polytopes. You can either describe them as the intersection of half spaces, or you can describe them as the convex whole of a finite set of points. And you can go back and forth as you like. Okay? So this is a polytope downstairs. So when you project the allocation rule x to get a reduced form, That reduced form is a convex combination of the vertices of this polytope. The main structural theorem says that every vertex of this polytope is the reduced form of a virtual welfare maximizer. Okay? So basically what we get is there's some point in the middle, and it's 20% of this reduced form of this one virtual welfare maximizer, 30% of this other one, and 50% of this other one. Okay? And now, because everything's linear, you just go back upstairs and you say, okay, well, for each of those three corners, let's look at the virtual welfare maximizer that induces them, and let's just take 20% of the one plus 30% of the other plus 50% of the third as proper allocation rules, and lo and behold, that distribution over virtual welfare maximizers, that mechanism, induces the same reduced form that we started with, okay, the same reduced form of the allocation rule X that we began with, right? So you project, decompose into the corner, decompose as a convex combination of the vertices, apply to the main structural theorem, and then go back upstairs and you're done. Okay? So proof by linearity. All right? Okay, so that's the first point. And then the second point is that if all we care about is our revenue, then the only thing we care about in our mechanism is its reduced form. We actually could care less about additional details. We only care about our mechanism in as much as we care about the reduced form. We already saw this. So when we first motivated the reduced linear program, we said what we clearly have going for us is that to express the revenue in particular, but also some of the constraints, the interim rules were enough. So we're going to use that again now. So corollary. There exists a revenue maximizing auction that is distribution over virtual welfare maximizers. Why? Take an arbitrary revenue maximizing auction, apply this corollary to get a possibly different auction, which is a distribution over virtual welfare maximizers and has the same reduced form. By virtue of having the same reduced form, it has the same revenue, so that is also an optimal auction. Okay? So give me an arbitrary optimal auction, I'll show you another one that's a distribution over virtual welfare maximizers. Okay? And this basically, this is great. Okay? This is really, probably a hues closer to Meyerson's theory than we probably had any reason to hope for, seeing those crazy examples last week, in my opinion. Okay? So I find this sort of very satisfying. All right? Okay, so that's this. So this fact is sort of the main takeaway, really, of this lecture. All right, so you do have a multi-parameter analog of Meyerson's theory, at least for these additive problems subject to feasibility constraints, although there's been some further generalizations over the past year. So you do have to have a distribution, we know that, and you don't get an explicit formula, which is not surprising, but beyond those two drawbacks, you get the same structural understanding of optimal mechanisms. So any questions about that? I do want to sketch the proof of the structural theorem. Yeah.
Just a quick, if we're distributing over different mechanisms, that
right.
means we just take our allocation rules and 20% of the time use this.
Exactly.
Okay.
Exactly. And you can flip all the coins at the beginning.
Yeah.
Right. And so I hope this was clear. But so where do these coins come from? They come exactly from the coefficients on the corners of this polytope down here.
Tell us why. So.
Yeah. Yeah. So this is not obvious. I mean, this is what's interesting. This is the interesting part. Well, maybe conceptually, this is what's really, the reason this is interesting is this gives you this, right? And this, but this is not that hard either. I mean, it requires a proof, but it's not that bad. Good, other questions? Okay. All right, so proof of structural theorem. Right. Okay. So consider any vertex of y. Okay. So some corner downstairs. All right. So one thing which is intuitively clear and not all that hard to prove is that you can characterize the vertices of a polytope in the following way. Okay? So think about linear objectives. So in other words, directions of optimization. Okay? And think about it like you're maximizing. Okay? So if you're maximizing a linear function over a polytope, you basically want to go as far in the direction of the normal until until there's no longer an intersection with the polytope. Right? So you can imagine like a sweep line, and when you get to the end of the polytope, that's where you stop, and that last point in that direction is the maximizer over the polytope. Okay? So that's going to be a corner. It's going to be a face, certainly, and sort of generically, it's going to be a corner. And in fact, corners of polytopes are characterized by this. So if you say, consider a polytope, consider the set of points that arise as the unique maximizer of some linear objective function, that subset is exactly the vertices of the polytope. Right? Which makes sense, right? So if something's sticking out, then you just pick the direction to go as far in that direction as possible, right? And then conversely, if you don't have that property, it must be because you're in the interior of some face, right? So we're going to use that property. We're going to use that property that vertices of a polytope are characterized by being unique maximizers in some direction. So let W be a linear objective such that Y star maximizes it. And so, just to be clear, what's the objective function? So the variables, right, are the y, I, j, v, I. So remember, the payment rules are not relevant here, right? So we're just looking at the y's. These are the variables. So, w is indexed the same way as the variables, right? So we're going to have a w, I, j, vi, and then we sum over all of the relevant stuff. So sum over j and u, sum over vi and vi, and sum over I in n. Okay? So this is just w transpose y expanded, okay, over the relevant index sets. Okay. Now here's sort of the sneaky part. So from these weights, let me extract a virtual valuation function. Okay. So define, so remember what I'm trying to prove. I'm trying to prove that y star arises, in effect, as a virtual welfare maximizer. So to prove that, I need to come up with these fees, right? And the fees are unrestricted, can be whatever they want, but they got to come from somewhere. And it's going to be this direction of maximization that I get them. So define phi ij to be equal to the weights. And again, I have to do this thing where I translate between the conditional and unconditional chance of winning. So I'm going to scale back up by the probability of this type. Okay. So this is just the usual prior. Okay, the probability that I's type is vi. Okay. Okay, so hopefully it's clear sort of where I'm going, right? We have our y star, I suggested a phi, so evidently what it would seem I'm going to argue is that the virtual welfare maximizer corresponding to phi has the reduced form y star, right? We started with y star, I needed a VWM, for VWM I need a phi, I just told you a phi, so that's how this is going to go down. So, all right. So what's the easiest way to argue this? Well, what we're going to do is we're going to say basically, give me any allocation rule. The claim is its virtual welfare with respect to phi boils down to this quantity. Okay, and again, so you may wonder, like, what is it non-trivial that I'm doing? Like, what has to be argued? And again, it's just keeping track of what's upstairs and what's downstairs. Okay, keeping track of the allocation rules and keeping track of the interim allocation rules, right? So y is just with respect to the interim, and virtual welfare maximizers are upstairs. Okay, they're real allocation rules. So, but the claim is, for every allocation rule x, whether it's explicitly maximizing with respect to phi or not, can write its virtual welfare, again with respect to this choice of phi, as, well, so first just by definition, you know, what is it? So we average over all possible valuation profiles. So this is kind of, well, let me just write it down. So we just expand, we condition on what the input is, and then on a given input, what's our virtual welfare? Well, we just sum over the bidders, sum over the goods, and then we look at who gets it and what's their contribution to the virtual welfare. Okay, so this is just by definition. So I'm treating phi as an objective function. Okay, x is an arbitrary allocation rule. I'm just saying how well does it do with respect to the objective function phi. This is how well it does. Could be good, could be bad. Depends on x. Now, we've seen this over and over again. Linear objectives can be articulated purely in terms of the reduced form. Okay, so this is written in terms of the x's, this is written in terms of the allocation rule. I can equally well write it just in terms of the induced y. Okay? So that's by linearity of expectation. So the expected virtual welfare, let me just separately look at each bidder i's contribution to the expected virtual welfare. So that's going to depend on what its type is. So I should look at the probability that it has a given type. And then, when it has that type, I should look at its contribution, okay, which should be this. So phi ij. Notice one thing that's really important is that phi ij depends only on vi. Okay, and I emphasized this back in the single parameter world as well, that the whole point of a virtual value definition is that I look at a bidder I look at its report, and without knowing anything else, I can map that to some new value. Okay, so again, it's crucial that phi ij depends only on vi and not v minus I. That's also what allows us to pass to the interim rules without any problems. And then this should be a yij vi. Okay, yeah. Right. So this is the expected, so what do we have? So this is the expected contribution of bidder I when its type is vi. This is its unconditional contribution. This is the total contribution. Okay. And so now it's clear why I defined the virtual values the way I did. Okay. So I've passed from the allocation rules to the interim rules. And now this is just the objective function value of the interim rule y with respect to this direction of optimization w downstairs. So again, this is just by definition. F times phi is equal to w. Okay. All right. So call this, where we ended up, star star. All right. Now, let's look at the first one, right? Suppose we wanted to make star as big as possible, okay? And we get to choose whatever allocation rule we want. Well, this is the same thing we did way back when we were studying Meyerson's theory, right? So basically, we were studying expected revenue. It was really hard to think about because, you know, you can say if you raise a reserve price, you'll do better sometimes, you'll do worse other times. It was hard to think about the prices directly. But then when we passed to virtual valuations, it was trivial to maximize the expected virtual surplus. You just maximize it point-wise. Okay? So whenever a valuation profile shows up, you just pick the feasible allocation with the biggest sum of the virtual values. We're in exactly the same situation here. Okay? So this is an average over valuation profiles. But I can choose the allocation rules. I can choose its output, its behavior on each valuation profile totally separately. Okay? So for each fixed v, okay, this is just a constant. So for each fixed v, I just look at what's in the parentheses, and I just pick the feasible allocation, whatever that may be, whatever the feasible set may be. I pick the feasible allocation that makes what's in the parentheses as big as possible. Okay? So like if it was unit demand bidders, I would just delete all of the negative virtual values, delete all the negative fees, and find a max weight matching on what's left. Or I just find a max weight matching. Okay? So if I want to maximize star, if I want to maximize star over allocation rules, the obvious thing to do, obviously the optimal thing to do is to just pick the virtual welfare maximizing outcome by outcome. Okay? Also known as the virtual welfare maximization allocation rule with respect to phi. Okay? So note, can maximize star pointwise using the virtual welfare maximization phi. Okay? So call this X star. Okay, so the allocation rule X star maximizes virtual welfare over all possible allocation rules. Okay, just because it does it pointwise. Can't do better. All right. But by virtue of maximizing this expression over all allocation rules, because of the equality between star and double star, we're also inadvertently, in this virtual welfare maximizer, we're inadvertently maximizing this final expression over all reduced forms. Okay? So remember, this equivalence holds for every allocation rule, optimal or not. Okay? So whatever you're doing, optimizing the virtual welfare, you're equally well doing maximizing the W weight of your induced virtual, induced reduced form. Okay? So, induced reduced form also, let's call this Y, also maximizes double star over Y. Okay? But what did we start with? We started with the vertex Y star, and we chose W so that Y star is the unique maximizer of that objective. Okay? So it must be that little y equals little y star. Okay? They're both optimal. So since Y star unique, Y equals Y star. Okay. And again, X is a virtual welfare maximizer. Okay? So we took an arbitrary corner of Y and I exhibited a virtual welfare maximizer that has that induced reduced form. And again, don't forget why we care about this. We care about it because it basically says all reduced forms are convex combinations of reduced forms. Therefore, all allocation rules are convex combinations of virtual welfare maximizers. Or sorry, all allocation rules are equivalent with respect to the reduced form for some distribution over virtual welfare maximizers. Therefore, so are revenue optimal mechanisms. Okay, so that's the whole story. So any questions about that? Okay. Let me just tell you briefly what I'm not going to talk about, but which I'm sure you're wondering about, which is computational issues. But this is just too much to sort of just fit into the remaining time of the last class. So let me just sort of mention it. So there's so I've been saying that the reason we care about this Meyerson theory was twofold. One was the conceptual structural, one was the computational. So now we have an analog of the conceptual structural part. We understand what optimal mechanisms look like. We understand the sort of added complexity which is necessary and sufficient moving from single parameter to multi-parameter. I've said nothing about the computational perspective. Okay, and it was perhaps worrisome even when we were just talking about the additive case and we had these border constraints because there were zillions of these constraints. So it wasn't clear how you were going to solve that linear program. On the other hand, we've been solving a lot of linear programs this quarter where at least one of the two between the variables and the constraints is small and the other is big. And that reduced form LP did have a small set of variables. Okay, so that's suggestive that perhaps we could use our ellipsoid magic to actually make some of these things, in principle at least, polynomial time. All right, so what are the things we'd like to know? So these are sort of the relevant computational questions, which you should be wondering about. So given a y, so given an alleged interim allocation rule, can you in polynomial time figure out whether or not it really is one? Okay, so I've given you kind of a structural characterization. I've basically said it is feasible if and only if it's a convex whole of reduced forms of virtual welfare maximizers, right? But that doesn't sound like a computationally efficient statement. Okay, so that's question one. So given y, how to check membership in y, i.e. is y in the convex whole of reduced forms of virtual welfare maximizers. Now, at the end of the day, what we'd really like is we'd really like to sort of compute the revenue maximizing mechanism. And so the high-level idea of how we might approach computing the revenue maximizing mechanism is we'd say, okay, well, x, that's way too many variables, so forget about solving an LP upstairs. But we have this, at least small number of variables, so maybe we can at least optimize over y, okay, and find the revenue maximizing reduced form, which is feasible, hopefully, right? So we have these feasibility constraints, and then we optimize. And then if we find the optimal reduced form, hopefully we can somehow, in a computationally efficient way, go back and find an x corresponding to that y. Okay, so the first thing we need to do is just how to optimize over capital Y. Okay, so if I don't worry about how to implement reduced forms and I just want the best one. Again, remember, revenue can be expressed purely in terms of reduced forms. So in principle, just working with reduced forms should be enough information to figure out what an optimal auction is, right? We just find the reduced form with the biggest revenue. Okay, so and then if we could solve this problem too, how do we actually figure out, again, remember reduced forms are not operational. Okay, they don't actually tell us how to allocate when evaluation profile shows up on our doorstep. So how do we take a y and make it operational and compute some x? So how to reconstruct a suitable distribution over virtual welfare maximizers. So the good news is we know that whatever the best reduced form is, we know it does have a conceptually simple representation. It's a distribution of virtual welfare maximizers. But then there's this question of how do we actually get our grubby little hands on it. Okay. Okay. So, right. So how do we do this? So it would take me, so the short answer is sort of the silver bullet here to all of these problems, more or less, is ellipsoid magic. Okay, so our main tool for dealing with optimization problems that have exponentially many constraints. And I do want to emphasize, so again, I'm not going to tell you the details, but you've seen stuff of comparable complexity in this class. Okay, so when we were talking in particular about the Levy-Swamy framework, so this was using scaling randomized rounding algorithms to produce MIDR algorithms, MIDR mechanisms, that had some pretty heavy ellipsoid-based machinery. And I guess that's close to the complexity of this stuff. So, it's the kind of thing where I could give another lecture and give you all the details. I'm not going to, but just don't be, if you want to learn more, don't be too scared of probing further. It's in the spirit of the kind of stuff we've been talking about. All right, so as you'll recall, the key point in the ellipsoid algorithm is, you got to implement a separation oracle. And so the really key problem, what things boil down to, even say for this first problem, just checking membership of an alleged interim allocation rule, is so if you give me a y, which may or may not be a member of capital Y, I want to figure out whether or not it is, does there exist a weight vector W, and think of W, think of all the entries in W's between -1 and 1, say, so that basically W transpose Y, so these are, I don't think I have that. Basically, so the value of this reduced form in this direction is strictly bigger than the max virtual welfare with respect to Vij, Vi defined as before. Okay? So let me tell you why this is a relevant subproblem. Okay? So the connection is the following. So I just erased what this is about. So suppose there was a Y. So you came up and you showed me a little Y. Okay, so an alleged reduced form, an alleged interim-allocation rule. And I wanted to prove that you're lying. Okay, so I wanted to show no way. Okay, so it was like one of the Sudoku puzzles. Okay, I wanted to do the same kind of thing. So one way I could prove that there's no way that your rule is legit, that it belongs to capital Y, is I could find a weight vector W. Okay, so again, this is all downstairs. This is all in the reduced form space. Well, I find a weight vector little w where the objective function value of your reduced form is bigger than the objective function value obtained by any reduced form of any virtual welfare maximizer. Okay? So let's recall the proof we just did. So what we just said is that every corner of the polytope, of the polytope downstairs, so all the corners of the downstairs polytope are reduced forms of virtual welfare maximizers. So that means, whatever direction, whatever W you optimize linearly downstairs, you're not going to do better than, you're not going to do strictly better than every single reduced form of virtual welfare maximizer, right? Because the corners, for every direction, a corner is going to be optimal, and the corners are exactly corresponding to these virtual welfare maximizers. Okay? So if you show me a Y, and I exhibit a direction where your Y actually outperforms every single virtual welfare maximizer, you're outperforming every corner of the polytope, so you cannot be in the polytope. Your Y cannot be in the polytope. Okay? So what this subproblem is trying to do, it's trying to find a certificate of non-membership of little y and capital Y. Okay? So those are the kinds of problems that show up as subroutines, as separation oracles when you apply ellipsoid magic. Now I'm not expecting you to see immediately how this gets plugged into here. I'm just saying, given your vague memory of the other ellipsoid arguments that we did, and given the kinds of problems that we're solving here, this feels like the kind of thing that would be likely to pop up, and it does. Okay, that's sort of all I want you to appreciate. Okay? And the reason I mention this is because if you want to solve, okay, so there's definitely some work, okay, going from solving this to solving these, okay, but it can be done. But what I want to sort of point out is that, even to verify that this was true for a fixed W, if you want to do that in a computationally efficient way, you need to be able to maximize the virtual welfare with respect to some phi. Okay? So forget about the even harder problem of sort of searching for a W that has this property. Okay, suppose I handed you a W on a silver platter and I said, this W certifies this infeasibility, and you just have to check it, right? So even to check that a given weight vector W works, satisfies the strict inequality, you have to compute the right-hand side, okay? So what I'm saying is, there's no hope solving these three questions in polynomial time unless, at the very least, we can solve the welfare maximization problem in polynomial time. Okay, that's the point I'm trying to make. So necessary condition can max welfare in polytime. Okay? Yeah.
So that's given this approach of using this structural thing to find this nice option. Like, this is not saying it's impossible to...
You're right. You're right. You're right.
We were saying maybe we could do it if we had a totally different way. We're saying given this method...
You're absolutely right. So in fact, you can... So it's excellent. So the point is that I'm only showing you an obstruction to this proof approach. I'm not showing that fundamentally revenue maximization is harder, although that is known. So you can prove in some sense that irrespective of your algorithmic approach, you can reduce, just in the usual computational problem sense of the word, welfare maximization to revenue maximization. Yeah. But it's an excellent objection.
And the complexity of welfare maximization is relative to the valuation complexity.
Yeah, or the allocation constraints, which are related, right? So I mean, so that's what's that's what's a little bit different about this formalism than the rest of the stuff we've been talking about. Normally, we've thought of the complexity as sort of built into the valuations. Here, there's this weird thing where, I mean, you know, we used additivity of the valuations when reasoning about this reduced form LTP about just it being sort of a faithful model pretty heavily. And so at least for, I mean, again, there's been sort of advances since, but at least for this setup, this way that we're going about it, you need the additive structure. And so then valuation complexity kind of gets translated to allocation complexity when you sort of shoehorn your valuation class into some weird additive subject to constraints kind of model. So, I mean, you can certainly imagine, right, but so the point is the welfare maximization problem need not always be tractable. I mean, it's easy to come up with cases where either because of the valuations you started with or just because of side constraints on the allocation, you know, yeah. So I mean, if you wanted to try to, yeah. So, you know, it may or may not be tractable, welfare maximization. But the claim, which again I haven't proved, I've only been trying to give you some intuition for why welfare maximization is necessary. But it's true that it is necessary, and it's also more or less true, and that's the content of the paper, that it's sufficient. Okay. So again, there's fine print here, which I'm not going to get into, but so theorem. Also more or less sufficient. Okay. So given as a black box an algorithm that maximizes welfare with respect to arbitrary coefficients, and then applying ellipsoid magic, you actually can, in principle, polynomial time way, solve all of these problems. Okay. Cool. So any questions about that? All right. So in the fall, I did a top 10 list, which I thought worked pretty well, actually. Because, I mean, one of the things about these classes is you kind of, at the end, you kind of forget all the stuff you learned. And, you know, like, or that, you know, like you still know it, but it helps to be jogged to memory and just being like, oh yeah, either that was cool or I can't believe I thought that was hard at the time or whatever. So, but unlike last code, I didn't prepare one in advance. So we can just sort of wing it. But do any of you have anything you want to make sure is on the top 10 list?
Ellipsoid magic.
Ellipsoid magic?
Yeah.
All right. Cool. Anything else?
The fact that laws in equilibrium corresponds to like integer solutions is pretty cool.
Yeah. So ellipsoid magic, WE exist if and only if LP relax is exact. Yep. Yep, exactly.
The way you can get BAC mechanisms pretty easily.
Yeah, the black box reduction. Yeah. Yeah, via fractional matchings.
Only countering it just to DIC.
Oh, okay.
Like just being like limits of what DSIC can do.
Okay, cool. Yeah. All right, well, yeah, let me just wrap up by sort of reminding you of the overarching course narrative. I mean, there was one, believe it or not. So let me just sort of, I know it like, you know, on a lecture basis it can be hard to keep track of. So, all right, so where did we start? So we started with really easy cases. And so in particular, week one, we focused a lot on unit demand valuations, which showed up again today, and the connection to bipartite matching. We covered the Crawford-Noer auction. So this was this ascending auction, where, you know, in each round, each bidder picks its utility maximizing good at the current prices and bumps up the prices by epsilon. We had a really quite non-trivial proof that that auction had some killer properties. So in the unit demand case, we introduced Corollaries and equilibria, and we had this great convergence between the smallest Corollaries in equilibrium and VCG prices. Okay, that was sort of the magic of unit demand valuations, and that was the limit, more or less, of where we had that property. And so what that meant was we had this really simple ascending auction, and by virtue of it converging to the smallest Corollaries in equilibrium, it actually was an ascending implementation of the VCG mechanism. So that gave us like an ex post incentive compatibility guarantee. So then we did the Kelso-Crawford auction, which I thought was cool for a number of reasons. That showed up a few different times. So that was the extension of the unit demand one to more general valuations. So that was how we motivated the idea of gross substitutes, although we later understood gross substitutes from many different angles. Initially, it was just proposed that the definition under which Kelso-Crawford would work. By work, I mean converged Corollaries and equilibria, again, assuming without justification sincere bidding. Okay, and then a couple lectures later, we said, well, what if there's no sincere bidding? Or what if we didn't have gross substitutes and we had a nice two approximation algorithm from it even for submodular valuations? We studied, those of you who went to the bonus lecture, we studied how gross substitutes can be characterized algorithmically. They're exactly the valuations where demand oracle reduces to a value oracle, which was sort of some very nice combinatorial optimization arguments. Then so that was sort of part one, ascending auctions, epic implementations, easy cases. So part two was DSIC. And with the problem, unlike in 364A, where I gave you this curated selection of solvable problems for DSIC mechanism design, here we really kind of confronted, we stared into the abyss, basically, for DSIC mechanism design. So we worked super hard to get, basically state-of-the-art, tractability results. So, one really powerful one, which was cool, was when we had a logarithmic copies of every item, whatever the valuations, we were able to get a 1 plus epsilon. That was using the Levy-Swamy scaling algorithms technique, and that was some of the harder linear programming machinery that we ever used. But we got a 1 plus epsilon in a pretty general setting. The other thing we did was this special case of submodular functions, coverage valuation functions, where we used a convex program within this strange randomized rounding, where you actually will sometimes throw away goods just to recover convexity of the objective function, but that gave us a 63% welfare approximation, which is the best possible assuming P not equal to NP for coverage valuations. So then we said, whoa, DSIC mechanism design is really hard. So when we can do it, the mechanisms are super complex, and a lot of the times we can't do it at all. So let's weaken the incentive guarantee and see what happens. And so when we went to Bayes-Nash equilibria, good stuff immediately started happening. There was the mentioned highlights where you have these very general black box reductions. You show me an approximation algorithm, I'll show you a BIC mechanism which is just as good. The only catch is that the running time blows up to depend on the size of the type spaces, but not in the same sense as we have in this lecture. So the sum of the cardinalities of the type spaces is your new running time dependence. But you preserve the alpha approximation algorithm, whatever it was. So then we moved on to part 4. So that was what's currently, I think, one of the hottest topics in algorithmic mechanism design, which is, take a complex environment like combinatorial auctions. What if you just throw something super simple at it? Just sell stuff on eBay. And we saw, I guess, two things. So first of all, lots of really simple auction formats have surprisingly good equilibrium guarantees, really equilibrium guarantees that are, in most cases, match or almost match the best known polynomial time algorithms for the underlying welfare maximization problem. And moreover, there's this very systematic way of doing these proofs. In the same sense, the price of anarchy proofs last quarter could be made systematic. So the notion of smoothness we saw last quarter reappeared today. We had extension theorems, this time for Bayes-Nash equilibria, a couple flavors. And we also had composition theorems. So at one point, we even reduced analyzing Bayes-Nash equilibria of a bunch of first price auctions to just analyzing the pure equilibria of a single item first price auction, which was a pretty great reduction in proof complexity. So then when we kind of mastered all that price of anarchy of simple auction stuff, that led us to the current topic, revenue maximization. Again, the main thing this has in common with the previous ones is that this is totally cutting edge stuff. Again, just what we talked about today is less than a couple years old. Very much still what a lot of people are thinking about, trying to understand this stuff better. We certainly saw the challenge. Right, we have these crazy examples with just one buyer and two items. Optimal mechanisms can be weird, but at least, as we saw today, we can get some grip on them using linear programming. There's even a multi-parameter analog of Meyerson's theorem. Optimal auctions are distributions over virtual welfare maximizers. So that's the recap. And believe it or not, you guys are now, if you sort of absorbed this course, I mean, you're amongst like the top 50 experts in the world in this stuff. I don't know if that's what you wanted when you started, but whether you want it or not, that's where you've derived. So I'll stop there. Thanks.